What is the probability that you can successfully assume an IAM role in a random AWS account? Well, I don't know. Why don't you tell us, Michael? Many resources on AWS can be configured to allow public access using their resource-based policies. S3 buckets are a well-known example, but there are other resources that can be made publicly accessible too, such as IAM roles. I'd somehow forgotten that this was possible with IAM roles. Scott Piper also maintains a list. Well, he doesn't maintain the list anymore, but it's still a good starting point for which resources can be made public. And you can see IAM roles are one of those. If you want to check those out, it's available at summitroute/AWS exposable resources on GitHub. So do check that out. The starting point. Well, let's get started then. When I conduct AWS security account reviews, every now and then I see an IAM role that has inadvertently been made public. This means that the roles trust policy has a principal in it. And as you can see, this particular trust policy does have a star in it. Such a policy sets forth that anybody with an AWS account can assume that role under the permissions of that role. From a shared responsibility model point of view, the responsibility for configuration is on the customer side. Obviously, the customer owns the role, and AWS shows a warning message on the console. But if you use infrastructure as code, chances are you will never click on that, and so you'll never get the warning message that Michael displays here. In any case, there is a dedicated note on trusting the star principle in the AWS documentation, which we'll have a look at now. As I've pointed out in the past, these blue and sometimes red boxes that contains these notes are a very good source of AWS security research, and everyone should be reading them because they do make a very valid point. After you create a role, you can change the account to star to allow everyone to assume that role, which is bad, obviously. If you do this, we strongly recommend that you limit who can access the role through other means, such as a condition element that limits access to only certain IP addresses. I'm not sure what kind of use case would allow that, but preferably you just limit who can access it without using a condition. And if you have to use it this way, I probably limit the permissions that that role has. So even if someone bad does assume it, they can't do very much with it. I asked myself how common this configuration issue is and whether it would be possible for external actors to find such roles without access to the underlying AWS accounts. That's a very good question, and I'm excited to find out how you're going to do it, Michael. To analyze the topic at scale, we require a list of valid role ARNs. And an ARN looks something like this. It contains an account ID and the role name. And so Michael obviously is going to try and find some of those. And he uses two approaches. The first one is SourceGraph. SourceGraph is a really cool tool to search public source code repositories and your own source code repositories if you happen to have some private ones. But they index all the big public repositories on GitHub. And various researchers, including myself, have used this technique in the past. You can see that Michael uses this query here, which looks for role ARNs. So you've got the 12-digit account ID there and the role name here, and across all of the global GitHub repositories that are indexed. At the time of collecting the data, the above query returned 86,000 results. After getting rid of some of those that are junk, there were 6,800 left. Those roles, however, only look valid, as Michael points out. They may not exist in practice. Michael has to confirm the existence of IAM principles without having access to the respective AWS account. And Michael points out that there's a really good way of doing this. Here, unauthenticated enumeration of IAM roles is described as a technique in hacking the cloud. This is how you do it. Basically, you just apply a resource policy to some kind of resource in AWS. You assign a principal who can access it. If that principal does not exist, AWS will actually throw an error and you won't be able to create that policy. If it does exist, you'll just be able to create the policy and everything will work fine. There's actually a tool called Quiet Riot, which allows you to do this at scale and across many resources. They don't just implement one sort of technique, but a variety of those that are very similar. So check out that tool if you want to do this for yourself. Okay, validating the collected 6,800 roles resulted in a list of 4,437 valid IAM roles for the data set. So now Michael has all of those roles which he can actually try to assume. The second approach he took was brute force. Given the well-defined structure of IAM role ARNs, it is also possible to just guess the account IDs and role names. So now Michael needs a way to get a bunch of valid AWS account IDs to be able to construct a role name. And he can do this using the same technique as previously with the resource policies, except this time instead of putting a role, he just applies this root principle, which just checks for the existence of that account. If it is possible to store a resource-based policy with this principle ARN, it means the account ID exists, and subsequently IAM roles can be brute forced to see if they exist in the same way as previously. Great. So using this approach, 1.5 million random possible account IDs were tested, which resulted in the discovery of about 139,000 valid account IDs. That's great. As a side note, which I found very interesting, is that if you test 1 million random possible account IDs, you will find on average 92 valid ones. I would have thought that the account ID space would be much more populated by now. Brute forcing valid IAM role names within those accounts comes with the challenge that the role names are case sensitive. So previously, using the technique from SourceGraph, you got the full role names, including what case they were in, whether they were uppercase, lowercase, etc. In this case, because you're trying to make up role names to test, you have to guess the case yourself. And the cool thing here is that Michael made a tool for doing exactly this, which is the IAM role name template expansion, which is just a very simple way to take an input like admin, and if you use an exclamation mark, it'll expand it this sort of way. So it tries all the different possibilities and gives you a list. When all of these base forms of IAM roles in the script are expanded, this generates a list of 30,000 possible role names. These names were tested against the 139,000 valid account IDs that Michael got in the previous step, and they resulted in 15,000 valid roles being found. It's lucky that regions didn't have to be applied because IAM roles are regionless. Adding the complexity of additional regions, etc., would have caused this testing to take much longer. In case you're interested in the statistics, here are the 10 most common IAM role names that were discovered. This is really cool. If you want to replicate this research, it's a good place to start with just these 10 role names. So obviously these are auto-generated or somewhat common for some other reason. The role assumption procedure. So once Michael has a list of roles that he wants to test to see if he can assume them, he needs a way to do that. And this is actually pretty cool. He does two specific things for his research. He sets a custom user agent. I don't know what it was, but it explains in the user agent. And he sets a session policy on the role assumption, which denies all access, which shows that if someone does an investigation of this activity, that he is acting in good faith. Even if he assumes a role, he actually can't perform any actions with it. He can only validate whether the assume role call worked or didn't, which is cool. So let's get to the results.
If you're enjoying this dramatic reading, I guarantee you'll love the weekly newsletter. So head on over to awssecuritydigest.com and we'll get it in your email inbox every week. Also, if you're weird like me and wonder what happens to all this cloud security research after we've read it, well, it goes straight into the Plarion Cloud Security Platform. You can get a free trial or a demo at plarion.com. I'm the super serious internet guy. Let's keep reading.
For dataset 1, the SourceGraph dataset, it was possible to assume 10 IAM roles out of the 4,400 tested, 0.2%. For the second dataset, which was brute force, it was only possible to assume one role out of the 15,000 that were tested, representing a much lower success rate of 0.006%. So what's going on here? Michael estimates that there was a much higher probability of decoys and canaries being present in the first dataset, which was published to GitHub. Researchers doing research on how attackers behave often put dummy or canary resources inside GitHub for researchers to scoop up and try. So Michael is suggesting that this might be the reason why this has happened, why the success rate is much higher. Where I was able to identify the owners of the affected AWS account, he informed them directly. Where he wasn't, he contacted AWS security. My personal interpretation of the results is that the numbers are not terribly high. Concur. Chances are that other kinds of attack vectors against AWS workloads will stay more prevalent. However, the research hopefully contributes to quantifying the risk behind this attack vector. I'd really love to see him, or anyone really, explore this a bit more with a much bigger corpus of AWS account IDs, and also attempting to find some further role names that might have a higher likelihood of being exposed in this way. You can, for example, posit that a role named public or test might have a much higher probability of being susceptible to this attack. Anyway, the remediation, as mentioned in the beginning, the underlying issue is basically a misconfiguration of IAM role trust policies. Not only IAM roles, but many other resources can be configured to allow public access by granting the star permission. In this case, it doesn't seem to be super prevalent, so there's not too much remediation to be done. But Michael does point to his very cool tool called AWS Lint IAM policies, which allows you to run a script against your accounts and find any issues that might be problematic. For example, this is an example results file. You can see here that there is a pass role with a star resource, and there's an explanation here. There's another finding here with a trusted policy with a wildcard principle, etc. So if you want to run this kind of analysis against your own account, I suggest you go check out Michael's open source project, AWS Lint IAM Policies. Just to finish up, a spectacular bit of research by Michael. Although it wasn't very fruitful in terms of findings, I do appreciate when people publish their research regardless of what the findings are, so all of us get to learn from them. I think the techniques that Michael used can be applied to a wide variety of AWS resources, and in fact, in the next few days, I'm sure you'll see a similar bit of research applied to SQS queues.